is regression analysis, and we talked yesterday about correlation and what it meant for one variable, an explanatory variable, to correlate with another. I emphasized the fact that when we're doing regression analysis, we never ever use the term one causes the other. We just don't have enough data yet to make that assumption or to make that conclusion. We have to wait till we get all the way to confidence intervals and significance testing to be able to say, hey, we're confident that A causes B. Here, we just say that A is correlated with B or A is not correlated with B. And the regression line is a way for us to understand how well that correlation works, and also it allows us to make predictions. I think in science class, when you talked about a regression line, that was one of the most useful parts of the regression line, is it could help you predict a certain value. And we'll see how that works here in just a little bit. Let me flip up some screen, the slides here, and we'll go ahead and get started. All right, so you should see on the screen, hey, Jalonzo, you should see on the screen the definition of a regression line, which I think it will be a little bit familiar with you. It's very familiar in terms of this is very typical Algebra 1 type scenario, where we've got values on the x-axis and other values change as x changes. They go up or down, and that's exactly what a linear function describes, and we're familiar with that from way back in Algebra 1. But a regression line tells us exactly how the response variable changes as the explanatory variable changes. It's the definition of a linear function from back in Algebra 1. And we'll use it to predict values of y for a particular value of x. And that's what I've kind of highlighted in this graph here. If we wanted to know what the value of fat gain is for an exercise level of 400 calories, well, then we can, if we've got the graph, then we draw a vertical line up until it intersects this regression line, and then we draw a horizontal line over, and then that's our prediction. Now, for right now, we're gonna talk about the regression line, and without really talking about how we create it or calculate it. We're just going to say, oh, we have this regression line, and it is our best representation of how the x values correspond to the y values on average. In other words, here's an x value here around 600, and that y value corresponds to, I don't know, a number like 1 or something a little less than 1, which is it's a ways away from what the prediction line or the regression line would indicate. But when I take all of these differences in total, this red line minimizes those differences from here to the prediction line. And we'll get into that detail a little bit here in a while. But for now, we'll just assume that we know how this regression line came to be, and we're going to say that it is the best predictor of Y values of fat gain for non-exercise activity in this range, okay? And again, we would remember our discussion from yesterday. We would describe this scatter plot with a moderately strong negative linear association, and there are no apparent outliers. There's nothing sticking out way over here, or there's nothing sticking way out up above this regression line or really far below it. So that's how we would describe that line. What we want to do is we want to define the way this line is described. And you'll see the regression line in the format of y hat equals a plus bx. Y hat is the value for the response variable on the regression line for a particular x value, again, just like a linear relationship. We're going to call b the slope or the rate of change that y is predicted to change with a unit increase in x. And a is going to be the y-intercept. It's the value predicted when x is equal to 0. All of that's just like Algebra 1. So it's very familiar to us. The terminology and the way this looks is a little different. And there is a reasonably good reason that we rearrange this. You're familiar from Algebra 1, y equals mx plus b, where the slope and the independent variable or the explanatory variable go first and the y-intercept comes second. But honestly, it's really just a convention. And when we take a look at the calculator in a little bit, there are two ways to display the regression line. Doesn't really matter which one you pick, but I will tell you, when you look at the formula page, the formula you'll see for the regression line is a plus bx, and it's just the standard form in statistics for representing a regression line. And and you'll notice we've got this terminology of y hat, and it is exactly what we remember or what we've come to expect with p hat. It is a point estimator. Y hat is a particular value on the regression line for a particular value of x. And so it is the estimator of the response variable at a particular value of the explanatory variable. So in that regard, it's very similar to what we understand with p hat. So we should get pretty comfortable with this y hat terminology and description here. Now, one of the things that I need to point out, and we'll see this in our example with the used Hondas in a little bit, that A is in fact the y-intercept of the regression line. It is where the regression line crosses the y-axis when x is 0. However, when we interpret the data that we get from this regression line at x equals 0, the value for A may not have any real practical meaning. In the range that the regression line is created, the slope of the line has a practical meaning, the value of y hat has a practical meaning. But when it comes to interpreting and understanding the Y-intercept, I mean, we can always interpret it in terms of it's the value of the prediction line when x is equal to 0. But in the real world, it may not have a practical meaning, and so it may not make sense. But we could still interpret it in terms of it's the value of the regression line when x is equal to 0. And so if you're asked to interpret the Y-intercept, that's what you'll do. And it is certainly acceptable. If it does not have any practical meaning, it's certainly acceptable to say that the value for A is not meaningful in this context. But it is important for us to keep track of this value because it helps us calculate the predicted value. Now over here you see some other variables, B0 and B, beta 0 and beta 1, little b, B0 and B1. These are common variables for these two constants that you might see in other textbooks. I don't think you will see it used on the exam. I mean, the formula sheet clearly shows you the form that you're going to use. So in our exam, we're going to see A and B. But if you take this course somewhere else, or you take another statistics course, you might see this is written as y hat equals beta 0 plus beta 1 times x, or b 0 plus b times x. Those are just conventions in other textbooks. But in AP Stats, I think the College Board is pretty much standardized on A plus BX. But just in case you see that in another class in the future, I thought I would throw that out there. So as I said, we can use the regression line to predict values, but there's a limit on our ability to predict. And this notion of extrapolation is using the regression line to predict values far, and I'm gonna highlight the word far here because I want to emphasize that extrapolation is using the regression line to predict far outside the interval of values used to calculate the explanatory variable. So I kind of sketched something here. Here is the useful range of the prediction line. The far end of the explanatory variables to the left here, the smallest explanatory variables, and the largest explanatory variables. Anywhere in between this left post and this right post, it is perfectly acceptable to use y hat as a prediction line. But the minute you step outside in either direction, either far to the right or far to the left, you're extrapolating data. And in statistics, that's really a bad thing to do because you don't know how the data behaves, how the response variable behaves outside of this region. It may become nonlinear and be curved out here, or it may curve downward, or it may take on some other sort of shape. And so it is improper for us to extrapolate beyond the range of data that we have used to calculate this prediction line. Now, if it's 1% past this, or maybe 5% past, it's probably okay. But once you get much farther outside of that, you're going to make a statement that this is extrapolation using the regression line to predict well outside the range is called extrapolation, and a prediction in that range is likely not to be accurate. Or I guess to say it more affirmatively, is likely to be inaccurate. So we just don't want to be caught, calculating or performing extrapolation on our data. We want to stay within these boundaries. Another thing that's important about the prediction line is how far the individual response variables are away from the predicted line, okay? And so this predicted line is the best fit between all of the red dots. It takes into account and it minimizes the difference in these residuals. And it does it in a way that we're very familiar with. If we think back to when we calculated the standard deviation, we squared the difference between a value and its mean. Well, what we're going to see in a minute is this regression line, y hat equals 16.3 plus 0.0908x, is calculated by minimizing the squared differences between each of these actually observed values. The red dots are observed values, and this line. Now, the good news is you don't have to do that calculation. Your calculator would do it for you. In the case of our test, I think they're going to give you either the regression line, or they're going to give you data that will allow you to calculate it using a 4-function calculator. Now, your scientific calculator will calculate it just fine, and I'll show you how to do that. But you won't be expected to do that on the test, but you will be expected to be able to interpret, okay, what does this mean? Here's the Y-intercept, and here's the slope or the rate of change for this particular value. Let's see what this graph is. Oh, this is back to the body weight versus pack weight for hikers. And so what we found was a hiker with a low body weight also tended to carry a low pack weight, and that makes sense. Smaller people carry smaller packs, okay? And so when we calculate this regression line, here's an example of where the Y-intercept really doesn't have a practical meaning. Our X variable here is body weight for a hiker. And so what this Y-intercept means is it's the weight of it's the predicted weight of a pack carried by a hiker who weighs 0 pounds. Well, that has no practical meaning. You can't have a hiker who weighs 0 pounds, but nevertheless, it's still the Y-intercept. And if we scale this, these X and Y axis all the way back to 0, 0, this line would cross at Y equals 16.3, even though it has no practical meaning to us. But the most important thing is, what is this thing called a residual? And the residual is the difference between the observed value and the predicted value. And it's represented by this vertical line from the actual data point down to the predicted data, the predicted line. And in statistics, especially in AP statistics, there's a really good way to remember what the how this residual is calculated. It's calculated as the actual minus the predicted. And in statistics or in AP stats, it's easy for us to remember. actual starts with A, predicted starts with P. And so oftentimes we'll talk about the residual is the AP. It's the difference between the A and the P. So it's easy, should be easy to remember, or the observed value minus the predicted. The actual value always comes first. And it's possible for the residual to be negative. Here, this value here is a negative residual because the actual value is less than the predicted value. So this residual will be negative. And the reason we square the residuals is the same reason we did it with the standard deviation. If we just added these in terms of their value, the residuals, that sum would come to 0. And so we square it so that we can keep track of the size of these residuals, and we want to make sure that the average distance above the line is equal to the average distance below the line. And in fact, I think in the next graph, it's actually more about the average area below the line versus the average area of the residuals above the line. And that's why we call it least squares regression line. And you will not have to calculate this by hand. And you might have to interpret it, but part of that formula involves this summation of the squares of the differences of the individual values. This is the actual value. Yi is the actual value minus y hat is the predicted value. So we subtract those two, we square them, so we get a positive number, we add them up, and then at the end we will, I think I have the formula here, we'll divide by n minus, well, I don't even have it here because it's not important for us, but there's an 1 over n minus 1 out here, just like there was for the square root, not square root, standard deviation. So, but you won't have to worry about performing that calculation manually. What's important is that we go through and we understand how to do it and how to interpret it from the calculator. So the residual is the straight line distance between the actual or observed value and the predicted value predicted by y hat, the prediction line. A couple of other things what you'll need to perhaps remember is one of the ways we looked at some of these curves yesterday, where this data, let me just make a copy of this guy. Yeah, this guy here is clearly, this data is not linear in nature. And so it is not appropriate to try to fit a regression line to that value or to that set of data. And one of the ways to determine, sometimes it's hard to know whether data is linear in nature or not. In this case, it's obvious. Even Stevie Wonder could see it. But in this case, in some cases, it's not easy to tell. And so what we do is we use these things called residual plots. To help us understand whether a value, whether data should be used, a linear regression model is appropriate. And so what I want to show you is just this residual plot, and you might see this on the exam, and you'll see here's the original data, and then here's the residual plot. And what you see on the y-axis is just the value of the individual residuals for each of the data points. You'll notice the x-axis is exactly the same as the x-axis here. And oddly enough, if you calculated, if you used your calculator with this set of red dots, and you calculated the line, the least squares regression line, you would calculate an R value, a correlation factor of approximately 1 here. And if that's all we knew, we would say, oh, this is a perfect correlation. Well, no, a perfect correlation is when all of these dots line perfectly up on the prediction line. But it is possible to sort of trick the math here and come up with an R value equal to 1, even though this data doesn't line up on the prediction line. So one way that we can use to know that this should not be represented by a linear regression model is when we do this residual plot and you get a certain obvious pattern. What you want on a residual plot that it is okay is the data should be kind of randomly scattered about here. You want some dots above and some below, but it's in a random nature. And so when you have a residual plot that displays a clear pattern, and sometimes it'll be like a sine pattern, or sometimes it'll be just a single curve like this, or just any particular pattern here, we're going to say that that data should not be represented by a linear model, and that's our conclusion. A well-defined pattern indicates a linear model may not be appropriate, and that's clearly the case here. Okay, I think this is, okay, so yesterday we talked about calculating in our data on the used Hondas. We talked about calculating an X bar and an SX for this set of data, and an X bar and an SX for SY, Y bar and an SY for this set of data. One of the reasons we do that is we can use that data to help us actually calculate or determine the prediction line. And I think that's where you're likely to see this on the test. And so what do I mean by that? Well, let's go back to the formula sheet for just a second. You'll notice that y hat equals a plus bx. And we've got two relationships here that we can use. We can rearrange this relationship here. If we have the mean of the y values and the mean of the x values, and we have the standard deviation of x and y, and we have the correlation factor, we can calculate the coefficients a and b that go here. And so if I were to guess, if you were asked a question about regression on the exam, I think it's going to take this fashion where you're given a set of data, and I'll show you this tomorrow. I've got a really good example of this. I'll show you this tomorrow, where you get mini-tab output, and it gives you X bar and SX, and it gives you Y bar and SY, and it gives you R. And then you can now take all that data with a 4-function calculator and compute this regression line. And then they might ask you to make a prediction. They might ask you to talk about calculate a residual for at a particular data point. All of those things you can do with a 4-function calculator. And I'll walk you through a really good example of this tomorrow. But all this is saying here is that we can calculate y hat from these two sets of equations, as long as you have X bar and SX. And honestly, if you've got a list of data, if you've got a table of data like this, you can calculate X bar and SX and Y bar and SY. I don't think you'll be asked to do that on the test, because with a 4-function calculator and 11 data points like this right here, that'd be really time consuming. It would take up most of your time and not really cover much statistics at all. But if somebody was to show you this data and say, oh, by the way, X bar is equal to this value and Y bar is equal to that value, etc., then you could come and calculate the prediction line. And in fact, that's what I ask you to do right here. Calculate the slope and the Y-intercept of the regression line using the means and standard deviations of the data, miles driven, and price. And so to do that, we'll go to our calculator. And yesterday we talked about entering entering the miles driven and the price in one list and then the other. And then to calculate the means and standard deviations, all we have to do is go to calculate. And then in this case, we'll do 2 variable stats because we want to calculate X and Y at the same time. And then X list will be L1, Y list will be L2. And so this will give us X bar equals 50.45 and SX is going to be 19.27. And then if you scroll down, notice here in your screen, you've got a downward arrow. If you'll just push the down arrow button, you'll scroll till you get Y bar and SY. And so what I would do if I were working through a problem like this, I would just go over here and write those values, because now for question 6, all you have to do is plug those in here and calculate A and B. Now you have to rearrange this formula to calculate A, but you have X bar and SX, you have Y bar and SY. What you don't have yet is R. And so now I want to show you how to get that on your calculator as well. Again, you have to start from a list, L1 and L2. Once you got those entered, then you'll go to the calculate menu. If you look down here, you see linear regression. But notice this format is AX plus B. And the format that we typically use, or we exclusively use in this class, is A plus BX. So you always want to select choice 8 as your routine here. And then again, you're just going to enter L1 and L2. We'll talk about this guy here, the store regression equation. We'll talk about that in a little bit, probably tomorrow. For now, I just want to show you how to get R. And when you hit calculate, it gives you A and B. So you already know what A and B are, but I want you to go through in question 6 here, I want you to go through recalculating A and B using these values, because quite honestly, that's how your calculator does it anyway. But and then the R value is listed here. R squared is going to be important to us, and I'm going to stop here at this point, and we'll pick up talking about R squared tomorrow. It is a really, really, really important value. But we need to have a little bit longer discussion than I want to hold you today. So you can calculate R. Now, I want to warn you, some of your calculators, when the calculators get reset or when the batteries get taken out and everything goes back to default, you may do this calculation, stats, calculate 8, and may go through all of this. And you may not, you may see A and B, but you don't see R and R squared. It's kind of a crazy thing, but if you don't see R and R squared here, what you need to do is you need to hit the mode button, and you need to cursor down to the second screen where it says Stat Diagnostics, and you need to cursor over. I'll just show you. I'm going to turn Stat Diagnostics off here. And I'm going to quit out of here, and then I'm going to do this calculation. Calculation 8, L1 and L2. See, it just gives me A and B with Stat Diagnostics turned off. So if your calculator at home doesn't show you R and R squared, go to the mode button, cursor down to the second page, and find Stat Diagnostics, turn that on. For some reason, when the calculator gets reset to its default status, Stat Diagnostics is turned off, and so your calculators may not show you what you want. So now, when you go through Stat Calc 8, L1, L2, calculate, we'll get R and R squared. So what you should be able to do now is you should be able to walk through everything through question 1, 2. You can identify the regression line now. You can predict the price for a car with 50,000 miles. That you just plug in the Y hat, you plug that in, plug 50,000 in for X. However, notice that your explanatory variables is in terms of thousands of miles. So when you plug in X, you're not going to plug in 50,000, okay? And then you're asked about making a prediction at 250,000 miles. And then calculate the residuals for each case, okay? So what you'll do is for each of these values, and honestly, you don't have to do it for every case. You can just do it for a few of them. You'll just take the prediction line, Y hat equals something something, AX plus BY, and plug in 22 for X. And whatever value for Y, you'll put that out here as Y hat. And then you'll subtract those two, and you'll do A minus P, right? Actual minus predicted, because this is AP stats. And then that difference will be your residual. So you can just go down through here, calculate a few of the residuals. There's a way to do it on your calculator, but again, you're not going to need to do that for the exam. So I'm really not going to spend a lot of time right now, because time is precious here at the end, going through all of that. And then question 6, you can talk about, you can go through, now that you have R and X bar and Y and XX, SX and SY, you can calculate the prediction line. And one of the reasons I ask you to do this, it's kind of selfish, honestly. Back before scientific calculators, this is what we had to do to calculate this value, okay? And we had to calculate R by hand. And it was tedious. It was really, really a chore to do. So I really want you to just kind of walk through this backwards, because quite honestly, I think this might be something you're asked to do on the exam. So in the used Hondas exercise, you should be able to complete everything through question 6. Question 7, we'll talk about it tomorrow. You'll not be able to calculate the standard deviation of the residuals using a 4-function calculator, so you won't be asked about it. But we will talk about what is prediction error, because we've already talked about standard error, and these two kind of have a similar meaning, and so you might be asked about that on the exam. But for right now, we'll stop for the day, and we'll leave it for you there and give you a chance to do a little work. Again, we're past the end of school. I'm not taking any grades, so it's really you're on your own as to how much you want to do here. But I'm not asking you to do something that doesn't help you prepare. And let me say that in an affirmative voice. What I'm asking you to do, I think, will help you prepare for the test. And I want you to do well. So if you have the time, go through and work through those things. If you get stuck, don't labor on it for 15 minutes. If you get stuck and it takes more than 5 minutes, just stop. My plan tomorrow is to go through the solution, and then I'll give you my solution at the end of class. But I want to kind of talk you through some of the calculations tomorrow, and so we'll do that tomorrow. All right, any questions? Addie, good to see you join us, and thanks for chiming in, for signing in, and maybe you guys should get on Snapagram and see if you can stir up some of these people. Get Gracie Wharton out of bed, and Briley. I haven't seen Briley in days. I don't know what she's doing. So just invite some folks to join us. Make it a little more fun, I guess. Anyway. Y'all have a great rest of the afternoon, and I'll see you tomorrow. Take care.
See you.